Hello, I'm Philip Meyer. Welcome to my video blog. In this video I show you around in the vector graphics interface. That's a vector graphics framework I created specifically for laser projectors and cathode ray tube-based vector graphics displays. I've created some examples for you I want to show you, and I want to show you how you can use the VGI the vector graphics interface in your application. So let's have a look. This is the setup we will start with. I have a Tektronix 603A vector monitor. So this is basically something you could place next to some measurement circuit or oscilloscope, whatever. And this is a storage monitor. It has storage capability. It can actually store images, and the way it does that is really tricky. And back in the days they had these to store images in cathode ray monitors. I can crank the intensity a bit, and here you see that these lines, they are now stored in an analog way inside the phosphor itself, so they are physically stored, and one can erase the image again and start over again drawing stuff. That's a nice capability we can also exploit with the VGI system. I will show you later, but for now we turned it off. So that's the vector monitor that has X, Y and Z inputs, and they were used as a replacement for plotters. Basically, back in the days you had possibility to hook up plotters to measurement circuits, and they would plot a graph and for very slow signals, and so that would be that was a thing back in the days. And so they also had these monitors, so where you had to use paper, or you can put it somewhere next to your oscilloscope and use it as a storage screen for watch the signal and whatnot. So we use it for vector output today. And then I have the EasyLace USB, and I suggest we take a look at this one now. So this is the inside of the EasyLace USB I use here in my project. This is basically a little microcontroller PCB with some digital analog converter and operational amplifier that drives the LDAR port here. These EasyLace USB devices are very common in Germany. Many laserists are using them with different software. It's supported by LDS and HE laser scan, all these stuff. And even purple scan, and it ships with very easy to understand examples. So Miller Electronics did a really good job here supporting programmers. Unfortunately, there is no Linux driver available. That was the reason why I had to go for Windows. But anyway, these also supports DMX. I added these option myself, so I don't know if they sell boards or so. By the way, they are really good at their support. I just wrote an email and asked them how to what's the pinout of these and how to add the DMX, and they immediately replied with some PDF. So that's pretty cool hardware, and they are ported very well. Unfortunately, these particular devices, I don't know, it's EasyLace 1 or 2. I don't know. They have a new line. I guess that's the EasyLace 2. That's their new one. So this is basically out of support now. I don't care. I can still use it for my stuff, but for the new software, if you want to use it with their new latest software they ship, that's the LDS Dynamics, then you have to get a new one or upgrade it somehow. I don't know how that works. I'm happy with the old ones. They work for me perfectly well, and that's just good hardware. I like to use it. And the next we have is this little converter box that converts the LDAR signal to a single-ended signal for the vector monitor. So let's look into this one now. So for oscilloscope screens, there is usually a single-ended input common. So I made this little box of tricks here, which converts the differential ILDA signal that's coming from the ILDA port into a single-ended signal. And the way I do it, it's just 3 operational amplifiers. These are differential amplifiers, and that converts the signal into single-ended. And here, these 2 caps here. Third one is of course the Z that doesn't need one, but the X and Y, they had caps, so that's in the resistor, so that's my low pass, and that filters out any sort of high frequency noise. So, and then I have 3 pots to adjust the dimension, and yeah, that's basically it. And finally there's the PC that runs my VGI system. On the Linux side, the applications, and the library that does all the rendering jobs. And on the Windows virtual machine, there we have my layer 3 implementation for the EasyLace USB. And last but not least, we have a laser projector here. I will not take this one down now and show you the internals. That will be another video. This one needs calibration, and when I do that, I will of course film it and show you. But for now, you have to live with the fact that you will only see the output of this machine today, not the insides. So now you have a rough overview about what we are dealing here with. Before we move on, I want to explain you some of the insights of the VGI system, and how the different layers work, what their purpose is, and all this stuff. So now we move on with a little bit of gray theory. So that's a long way. That's the way the data travels down to the vector display. So it starts with your application. So that's where basically you are sitting as a programmer. So you are calling functions like VGI line, for example, to draw a line, or the initialization functions to initialize the system. And all these functions, they are implemented in the layer 1. So basically you are talking with the layer 1 all the time, drawing jobs basically. And the layer 1 then generates a code. So that's code that looks a bit like assembler, but it's basically a clear text instruction that is meant to be transferred to the layer 3, the very highest layer in the system. The code, the VGI code, is handed over to the layer 2T that does the network handling. So it just this layer 2, T in air, these layers taking care that your VGI code can travel safely through the TCP/IP connection. So that also means that your system that does the displaying stuff that can be in a remote location. Not too remote, because this protocol is not latency optimized. It should be a low latency connection to have a good real-time output. That's the job of the layer 2 T and R. And on the R side, so basically this is basically a border, so your Ethernet cable is separating that. So this has to run on one PC, and the very rest also has to run on one PC. But there it's basically on this level, it's internet basically. So when the VGI code arrives at layer 3, it gets passed there. It gets buffered there. So there's a buffer that will buffer all the instructions once they are passed, and then it will hand it over to some display. In my case, so that's now it's getting hardware specific now. In my case, I hand it over to the EasyLace driver. That I think it's the EasyLace USB DLL or GM laser DLL. I don't know anymore. So that's the DLL they ship with their their hardware, and that talks to the EasyLace USB hardware via USB, obviously, and the EasyLace is connected via an ILDA connection to your XY display. And ILDA, that you already know, is just an differential analog interface. So pretty simple. I mean, you can always convert it to single-ended and hook it up to an oscilloscope. So that's basically how the system works. And now let's. I think that's enough theory for now. Now we should look into some practical applications now. So this is what you should have once you've downloaded the VGI stuff. Here you find examples. You find the HPGL to VGI compilers. That's a compiler that enables you to convert HPGL graphics into VGA-C code. You can use it with Inkscape, so you could in theory draw your graphics in Inkscape, convert them, and use them in VGI. So that's one of the supports. We have the libVGI, which has to be installed on your Linux machine in order to make use of the functions. And the FC VGI2EL, can go into that. So I have a precompiled Windows, the Windows stuff that's precompiled. You can immediately use it, or refer to the source code and compile it yourself if you want to do so. So that's for the EasyLace. That's why it's called VGI2EL. And then we also have the VGI2SDL. So that's kind of a debug tool that's for basically simulating your output. So if you don't have access to your hardware and you want to develop, that's a very helpful tool. And I can show you how simple it is. So when you want to implement your own hardware and use it with VGI, let's say you already have some vector output stuff, you could use this code as a starting point, and it's really just this. So it does register a callback inside the so it uses the VGI with the callback. So the VGI does all the rendering for you, all the stuff. As long as you know how to draw lines on your vector display, you are fine. So you can immediately start using VGI with your own hardware. It doesn't necessarily have to be the EasyLace USB. So that's what comes with the package. It also has README files, and for example, if you look at the documentation of the library, you also find a description of the layered structure, and that's basically what I've shown you already. So I suggest you read through yourself, then you should have a good understanding about how the protocol works, and the examples I included. So there are lots of examples can show you here, and we will take a look at some. That should make it easy for you to integrate stuff and to learn, basically to learn how to use the VGI. So now I'll show you how to install VGI on your Linux machine. It's just simple. First you need to install the libcodebanana. So that's please refer to the description section. There's the links are there. That's my core library you needed to use all my programs I wrote in C. So install that first before you do anything else. So it's just simple, should compile without warnings. If you have problems there, just drop me an email. I do care about this. I do support people who want to try my stuff. And then you go, you do sudo make install. So, and then you need to type in your password. So, and then that's it, that's done now. So libcode bananas is installed now and ready to use. So let's now move on to the next one. Next one is the libvgi, and the procedure is the same. You just type make and it compiles, and then again sudo make install. And again password. So that's it now, it's installed now. So now we have the VGI, all the VGI gadgets ready, and now last but not least we also install the SDL2 VGI VGI to SDL, sorry, tool that enables us to simulate a vector graphics display on the PC screen. We will need that for debugging and testing stuff. So procedure is here the same. As you can see, it uses the libSDL and SDLGFX, so make sure that these are installed on your system. You can use Synaptic or whatever to do that. So if you do not have them ready, it will cause problems, then it won't compile and complain about missing stuff. So yeah, make sure that these are installed, and then you also can do install it like with sudo make install. As simple as it just installs it through user local bin. And now you already have on your Linux machine, you already have a working VGI system, and we could in theory also compile the examples. So let's cd to the directory. Okay, yeah, you see a little more directories to see unreleased stuff I want to release in the future maybe. So cd examples, and here we have them. Yeah, there's lots of stuff. I have a make file for them. Yeah, first let's do make clean so you see it. One important thing for the examples, if you want to try them, keep in mind that VGI is a network-oriented, basically a network protocol as well, and here you have this config H, so where you can set up basic parameters, and you should configure your IP address here. So that's the IP address where the display is located at, and before it's hard-coded before you compile. You should set that properly. If you are intending to use it only with the SDL stuff, then it's your local host, it's the right IP address, will be always fine. But if your VGI display is on a Windows VM, then you might have a different IP address, and that's, for my case, it's 192.168.100.106. So for you it might be different, so configure that before you compile. I mean, these are examples, so that's why I didn't include any command line options or whatsoever, so you have to live with just setting that properly. So just saying, because you might be, stuff might not work because the IP address is set wrongly there by default, most probably. And yeah, then you just compile them and it should run through. There's one thing. You also can compile them individually, right? CDing into the directories, that doesn't matter. One thing I didn't show yet is how to install the the HPGA compiler. That's the Python script that needs to be installed because it's called by one of the make files. The HPGL example calls that. That's the output from it. So you need to install that as well. We have one sec. The HPGL2 VGI compiler is here, and that's just the Python script, and the CSV makefile installs it, so it's callable. I can show you real quick. That's one script that doesn't use much at all. It's just using normal stuff. It's pretty simple, just generates a C code then. So you have to have this in place to run the makefile in one go, because it will complain if you don't have it. So, but anyway, it doesn't matter. You can always CD into the individual directories, and then you can use the applications individually and compile them individually. So yeah, that only as a side note. So next we look at a typical VGI application and how it's set up. So this is the clock example. The clock example is basically something like a digital scope clock. Don't expect too much here. It's just basically a simple string that shows the time. So, but for starter, it's very simple and good to understand, I think. So that's why I start with that. So first we need to initialize the VGI interface. So we initialize the layer 1 here. So that gets the basically size parameters and some aspect flags. So these aspect preserves, that means that it preserves the aspect ratios. So I suggest for that you have a look at VGI L1H. So there are these this the naming convention here. The layer 1 and layer 2, they are all named like VGI L1, and you need L1 and L2 for the basic application. That's all you need. And yeah, you give it this basically size parameter and initialize the basic stuff, and then you initialize the network layer by doing the initialization of the layer 2T, and that gets always this pointer to your display struct. So that's your display here, and you give a pointer and the display IP. So that's the IP you have seen in the header file I showed you before, and that's the port. Of course, I have no IANA reserved port. You just choose one. I choose 1, 2, 3, 4 here all the way through, so you can do the same or choose something you like. The one at the end, so all these functions, at the end, the very last parameter, in almost all cases, that's the verbose flag. So if you set that to 1, you will get debug output, so you can create debug traces and see how your program causes problems in the productive use. Of course, you set it to 0, so it generates no output at all. And here we have a while loop. That's also pretty simple. Just gets a timestamp by get Unix timestamp. That's a libcode bananas function that gets you a Unix timestamp. Nothing much behind it. The Unix timestamp to string that converts it to a readable time string. That's basic stuff. I know there are in Linux, there are already things to do that, but I abstracted that because I found it too difficult all the time messing around with stuff. That's way easier to do it. Yeah, and then you start by clearing the display first. So you erase the content of the remote buffer, clear them, and then you can use VGI text, and you see always gives the display pointer. And yeah, then you give the text, the X and Y position, the size scalars for X and Y, the clock string, and yeah, some formats thing. I would have to look that up, what it's exactly like. Let's do it now. That's the VGI layer 1 header file, and you can see where it is. VGI text, and you see you have the size parameters and X and Y size, the text, the format. That's some format flags you can issue, like center text and or do perpendicular text, something like this. A lot of things are possible. And for the VGI text, I have to mention something that's kind of special. All the normal functions, they all basically issue drawing jobs like draw a dot, draw a line, so very basic stuff. But the text is different here. It really transmits the ASCII text with the VGI code down, all the way down to the display, and the display is doing the rendering of the text. I've done that because I wanted to offload the protocol a bit. I mean, something like a text would result into a lot of polygons and lines, and that's why I let it do by the display directly. So the text is keeps that in mind. That's a little bit a special one. So yeah, and then your RGB colors, and then that's it. That's the text function you call here. And then you call VGI execute, and that causes basically the display to really draw, to basically, in the case of the EasyLace, and it would instruct the EasyLace driver to transfer the content of the vector memory through the USB into the EasyLace vector buffer or dot buffer. I mean, in the end, it's all dots, and the information if the Z-axis should be driven or not. And then that's a little bit messy here. I just do a sleep to slow the process a bit down, offload the CPU. In the case of a clock, that's not really a problem. For more complex stuff, you should use the integrated frame synchronization. I will show later. There's a possibility to synchronize frames and get basically controlled frame rates, but that comes later. That's basically it, and that's the whole thing. So then you have a clock on the oscilloscope screen. It's simple as that, and you could also add another text or draw some stuff. And I suggest what we can do next is I suggest to try it, and then we see how it looks on the oscilloscope screen. Okay. So in order to get ready, you should have installed your VGI2EL package on Windows. You do it just by copying. There's no setup. It's just simple. It doesn't even use the registry. It's just a simple Visual Basic application, and I already put all the redistributables right next to it, so you don't have to really care how to install them. All you need is your EasyLace USB. It needs to be in the system or System32 directory. Just follow the instructions Miller Electronics ships with the device. Just install it as you would always install it. I'm sure if you already have an EasyLace, you know how to install stuff and how to use it. So just get it ready. For me, I have to check it out. I have to plug it in virtually. So now I have it there. And now I can execute that. And here we have the tool that drives your EasyLace. So it has basically 4 of these thingies here, and we have a preview, so where we can preview the output, and you could also use that for the simulation. Just disable the flag here. Then it executes without touching the EasyLace driver, so you can use that for simulation debugging as well. You can create a debug output of your vector memory content, but beware that slows down, so it's disabled by default. You can monitor the VGI code instruction stream. You could monitor the network activity. So if there's something wrong, you have a lot of tools to find out where it's going wrong, and you have a log text to see what happens. And currently I've loaded the settings for the Tektronix. You can do that by import settings. I prepared some settings for my RayJack 35 Plus, for example. That's for my laser projector. So you can import settings, save the settings, and export them again, do all this stuff. You have two interpolators available. You have a simple line equation, so that just creates intermediate dots and can be configured with this granularity here. So that's basically the distance which it has to have, which has to cross until it makes an intermediate dot. That's basically disabled, by the way. 4000 is a lot stuff. Yeah, I can set it to 1, but be very careful with these settings. You can destroy a scanner with that, because if you omit the interpolator on a scanner, it just drives it too fast. So and that might ruin your scanner. So beware of these settings. So be really careful with that. I also included a README where you can read through, and for an oscilloscope screen it's fine. So that's good for practice. I can restore the configuration again, then it reloads it. I can do can configure a lot of stuff with port as well, the port where it listens. So the spot killer trigger, that's probably interesting for working with the vectrex. So that basically draws a square or something with a blank line to trigger the spot killer. So that basically that you see something. Otherwise, if you draw too small graphics on the vectrex or so, it will blank the screen to protect the CID. So that basically tells the vectrex analog circuits that the scanning stuff is still going on. So, and if you start that, it starts running and it starts listening on the port, and I would say we just start the VGI application on the Linux side now. I have to click here. So that's my application, and so here we are. It's already compiled, and all the examples compiled to the binary named VGI, and we can execute it. And here it says now that it's now successfully connected to layer 2R. Yeah, and that's it, how it looks on the Windows side. It's connected to port 1, 2, 3, 4, and let's look at the preview. So here we have the simulated display that also can be disabled, but it doesn't save too much performance, so you can also very well leave it on. And this is how it looks on the oscilloscope screen. Here we have our scope clock. Isn't that nice? So now we know how to handle text, so let's have a quick look how to handle lines. So in this example I just draw a square that bounces off on the edges of the screen, and the logic behind is pretty simple. You can figure out that yourself how it exactly works, but here I draw the 4 lines of the square, and it's simple. I give the display pointer, then I get the X and Y coordinates of the start point, and then the XY coordinates of the end point, and then the color. That's a simple, straightforward example on how to draw lines. I can start that now. .vgi. By the way, the Windows software now runs unattended. It automatically accepts connection, closes connections. And here we have the square that bounces off the edge. It's pretty simple. Yeah, looks nice. So now you see how simple it is to make a vector graphics animation like this. It's just a few lines of code. Of course, there's more. I mean, another important I will not show now, but there are a lot of examples on how you can figure that out yourself. Just have a look at the code. It's the VGA polygon. Polygons, in the sense of VGA polygons, are basically a list of points that are getting interconnected via lines. So you have an X and Y position, that's where your polygon is starting, and then the number of coordinates that follow, and in these two integer arrays, there's a list of points that you issue. The advantage of this is if you use Z, then the points are getting packed into one VGI instruction, so it's one instruction then instead of many. And the layer 3 in the implementation knows that these points are interconnected, and it will not, and it can handle that easier, because if you issue a line, then what VGI in the layer 3, at least the implementation I have in Visual Basic, is doing is it just draws the line, so it turns the laser or the electron beam on, draws a line, and waits a few microseconds to prevent overshooting, and then it turns it off and waits again. And if you have multiple lines, it doesn't know that these lines belong together, so you have all these intermediate periods. And if it's a polygon, you can optimize around of it, so it's just more optimal, and of course it's easier to handle for you in the code. And yeah, I think I demo a few examples now, and then we have a look at the VGI UT, the utility layer of VGI that is optional to use for you, but has some very nice features. This is something I made with Inkscape, and there I use the HPGL to VGI compiler. So that's something that uses the built-in utility layer together with the 3D engine. And you see these little round thing there. That's driving the safety of a laser projector haywire. So that's nothing that can be displayed on the laser projector very well. If you remove these snail, then it works, but that's just too bright. So yeah, that's what you can create. So here we have something I call mosaic graphics. So that's basically the way you use it is just you issue an ASCII pattern, a pattern modeled as an ASCII string to the VGI subsystem, and then it draws this mosaic pattern that is made out of squirts. I call it squirt because it's squirting in the Y direction over the screen and then in the X direction. And that's basically an optimized raster screen. It's a raster screen. It goes like serpentines this way, so that's how it draws the squirts, and then it goes that way around. On a laser projector that's a little bit too much, I must confess. But here on the oscilloscope screen I must say it looks very, very nice. And I use that for a game. I will show you later. So yeah, I can say it. It's for Maze War. It's the Maze War maze. So and here we have the individual squirts, so you can basically generate lines like these by just issuing ASCII strings and model the on and off sequences of that. So yeah, that you might find it useful. It's in the utility layer, of course. Yeah, and here we have a radar screen simulation that's made with just a VGI line, and then that's it. It just rotates. Here we can play with the with the start screen a bit. So that looks pretty nice. So I think the start screen and the VGI, that would be a good team if we could make it somehow controlled automatically. So the application would then press the button, draw something into the phosphor. That would be cool. Here I present an application that writes an image line by line into the start screen here. And that's basically how SSTV worked back in the days. Slow scan television. So, and if you wonder what's depicted here, it's just Ohm's law. The utility of layer of VGI also offers some basic shapes you could use with your project. This should be a rotating star. I made this with the utility layer as well. It's just 3 squares, so I just draw three flat squares, and then I just give the rotation parameters, and by that these star formation, star constellation here is generated. So we'll look into the code later. I show you how to do that. And I have, in this case, I have a controlled frame clock, so the frame controlling it's set to 20 frames per second, and that's what it does. So yeah, that's basically it gives me the full expected frame rate here. And here we have the same, only with a cube, and yeah, we get 20 frames per second. Yeah, here we have an example for text output. So that's the various text modes you can have, perpendicular text or the mirror text. So that's already built into the VGI system, ready for you to use. Yeah, here I have an application that just draws random dots on the screen. That looks nice on an oscilloscope screen. I don't know, on the laser projector. I hope it won't stress it too much. Yeah, it depends on the output speed you will have in the end. But yeah, anyway, it looks nice. Yeah, I promised to give you an insight of the VGI utility layer. So it's called VGI UT. You see it here. That's the header file you include, and yeah, let's open the file and see what's in there. So here it is. So that's the utility stuff, and it has basically two major structs here, and that's the one sec. Yeah, it models new data types. So we have, but the two major I want to point out is the polygon and the graphic, and the basically what the polygon is doing. It summarizes a list of vectors to a polygon, very similar to the VGIOT, and when plotting it also uses the VGIOT for plotting these structs. So it's a list of vectors, and the graphic that summarizes a list of polygons. So you can basically have the entire drawing in one VGIOT graphics type. And then it also has some more handy types for the vector, for the color as well. So it's basically an additional subtraction layer. But the VGI layer 1 and VGIOT, they do not interfere with each other. You can use them simultaneously. So VGIOT is only a helper basically for you to handle the whole system better and have more powerful functions. And it also includes this 3D engine. It's all vectors here are 3D vectors, and they can be rotated and stuff. And inside the graphics, there's always the position vector, so where you want to have your polygon or graphic appear. A pivot. The pivot basically gives the the middle point. So when rotating the pivot, it rotates around the pivot. And the angle, that's basically the rotation angle, and a color as well. And of course here the polygon, and here the polygons. So that's, here you see that's both the same. And so you do not necessarily need to have to draw your stuff in 3D. You can draw it as a 2D model and then rotate it into the right angle you wanted to have it displayed. That's the trick here. So that's the idea behind. So I want to keep all this mathematical rotation matrix stuff. I want to keep it away from you, so you can concentrate on your vector application. And so you have these core utils here. So there's a lot of stuff there. Alloc polygon framework that allocates you some space for new polygon. And you have copy functions. You can merge graphics. You can do all kinds of stuff. And here you find again these the line drawing function, for example, again the VGIOT line basically doesn't take the raw coordinates, it does take the vectors instead. Here you get the vect types there, and so that's basically another abstraction layer you can use, or you don't have to use it, but it's a lot more practical. And then you have supplementary utils I made public, but you should only use them if they're really necessary. Try to do everything by issuing the right rotation parameters and position parameters. Don't hack around in your polygon list afterwards. And then we have predefined shapes, so you can have a cube, can have a rectangular. So that's the cube I already have seen. That was the cube from the example. That's basically manufactured here. You always get a polygon or a graphic back, so you can manipulate that as you like later. Once it's manufactured here, you get it and you can manipulate it. It's not directly drawn. I have three angles. That's what I've seen in the shapes example. And here we have the squared pattern. That's what I meant. You get to give this char array, and then you give the length, and then you specify the car that should be detected as a basically electron beam on or laser on. and you have all kinds of functions where you can revert and invert stuff, so you can rotate it and so on. They need that for the mosaic pattern. So that's basically something here, the squared functionality I use the mosaic pattern. So the mosaic pattern is basically a squared on steroids. It just gets a mosaic pattern, then it draws something like this maze war maze you have already seen. Yeah, so that's what you have with the VGIOT powerful abstraction layer, and I use it here. So what I do here is here I create a star. So first I allocate the space, so because I need memory space, I need to allocate it. So you see right utilities there, so I do not have to care about the malloc. Of course I have to free it someday, but yeah, this returns the graphics. So you have free functions for graphics that go through the entire struct, and if there's something there, it frees. So that's pretty well automated. And yeah, then we define the colors, and then we define the flat squares. So you see that's just 3 flat squares, and then we set the position we want, and then we care that the pivot is in the middle, and yeah, in the end we issue the rotation parameters, the angles, and we are doing some scaling. So that's basically our factory that makes us these stars. So it's basically so to say a factory pattern, to speak in design patterns. And then we have again the normal initialization. Nothing changed here. Here I set the z-axis far, and so since there's a 3D engine involved, I need to tell the engine where's my horizon, so that it scales that it gets the perspective view correct. So I can basically by this I control the strength of the perspective deformation. If I don't set it, then we do not have any deformation at all. Then it's just disabled. So if you want this perspective thingy, it activates it by setting a far, and here we manufacture the star with our star factory, and here, yeah, that's a good point. We have this frame rate controller. I can explain it right here. There's an individual example for that, but it's also fine if I explain it here. So here we get a clock. This is the frame clock. We defined it previously up there. Frame clock T. So that returns you a frame clock. And then we clear the display as we always do. We generate the graphics. So basically that takes our graphics that contains the star graphic and displays it. So that issues everything that belongs to the star to the VGI utility layer, and that does the rotation and takes care about that the angles are correct and the positions are correct, and then it hands it over to layer 1, so you do not have to worry about anything. It does all that for you. And that's the clock OSD, the clock on-screen display, is to get the frame rate display. So that's basically for debugging, so to display the frame rate. I have it on here, but you could also very well leave it away. And here I add to the graphic, I manipulate the angle, and just by manipulating the angle it gets the rotation effect. That's all. So I increase the angle on every z-axis. On the z-axis I subtract it to get it a bit more exciting here, and yeah, that's it. And then I execute it, and then it executes. And here, that's where the magic happens. It synchronizes the frame clock, so it gets the clock pointer, and the function returns the function monitors the time and returns the number of dropped frames. And by knowing that, the application could react and basically skip certain frames. That's what it does here. It basically adds to this angle the skipped frames, and next time it runs, it just skips these frames. So it just starts at where it has to start. So it keeps it, so that keeps the basically the framing in sync. That's not always needed, but in VGI, if you draw something, if you issue something wrong, it just stays there until you erase it. So if you do not have any animations in your application, just think of a CAD program or something, then you would not need any synchronization or stuff. So, but I want to say VGI doesn't need any refreshing, so to say. Yeah, that's it. That gets you the star. That's all. If you use, for example, you have seen the example with the compiled HPGL code. You can look into that as well. Maybe you find that interesting as well. Oops, you're a bit too far off. Examples. HPGA polygons. So this is a little bit special because the makefile also works the HPGA compiler. So that's by the way the thing oh gosh, yeah, it's not very good to see because of this shitty pattern behind. And the camera seems not to like it too, but that's what I've drawn in Inkscape. So that's the SVG. I just exported it that as PLT file, so that's the HPGL inside. And what the compiler does, it outputs these two here. So the H file is the header file, there's nothing much in it, but basically it outputs such a factory that makes the polygon, the graphics. So that basically that's auto-generated by the compiler and returns the graphic you have seen on the oscilloscope screen. So you see it's a lot of stuff here, so it's auto-generated. And yeah, this auto-generating is fine, but you have to keep in mind, especially if you program application that should run on a laser projector, you have to be take care about things. The laser projector will not process any kind of graphics, so you have to think about the special physical display properties. That's what I want to say. So that's it. I think what I also should mention is VGI is not only suitable for writing new applications. It also can be used to equip old vector games or vector graphics with systems with a new output hardware. And I have this one here, so that's the WACX. So it's the patch is included, but not the code. The reason for that is that the source code here, the ownership is unclear, so it doesn't contain any licensing information whatsoever. So you have to, in the README, you find where to download it, but you have to do that then yourself. I unfortunately cannot include. If it were GPL or BSD, I would have included, but in this case, no. Here I have my working directory with the code, and in the WACX you find an OS int C file. So that's the C file here. The OS int basically probably stands for OS integration. That's where it renders the vectors on the SCL screen, and I hooked myself in there. I hacked myself in by adding a VGI line, and that basically outputs all the vectors that are generated by the vector game to the VGI system, and the system then takes care for the display. And the code is very hackish. I'm not really satisfied with it. I would have to go deeper into this emulator, which I don't want to do. So you have to live with it. I have a frame synchronization as well in here to skip drop frames. And in the beginning, when the Vectrex logo is displayed, it skips a lot of vectors because my subsystem with the easy layers and the Windows software is just not fast enough to process the Vectrex logo. So it's a good stress test. It's playable, it works, but yeah, probably I think of replacing the easy lays with something else for the faster vector screens. For laser projector, it's fine, it's good hardware, but for the oscilloscope display, it's a little bit too clumsy, and I don't know. I really don't know. Yeah, there has to be. I have to find some better hardware there, and I think, and there is some. Yeah, there's this guy Shamil Hudson who has done some work for restoring old vector games on oscilloscope screens and Vectrex, and he is working on a hardware, and I'm really looking forward to that. There's this, he calls it VST, so that's a vector output device suitable for these types of screens, and I think I will order one as soon as they are available and integrate it in my system to have a faster output for fast displays. So now let's look at the Vectrex emulation. Yeah, I have an optimized configuration here for the oscilloscope screen that runs the easy laser at the very max of its speed. So that's what I run now, and now let's load it up. So here it goes on now. So that's the Vectrex screen on the SDL, and here it's on the oscilloscope. And yeah, that's a pretty good stress test for the whole system, I think, because in the beginning the Vectrex is really pumping a lot of vectors to draw the square here. So, and here you see the frames per second display. Now you see it going up as soon as it displays less. There's unfortunately a little bit too much reflection in the screen. There's no anti-reflection on this oscilloscope screen. That's not so good. So here we see it. I mean, it's okay. I'm happy with it. I get a playable game, but it could be faster. It's unfortunately a little bit difficult for me to play it with one hand, while the other hand is holding the camera. But I can at least try. Oh yeah. Yeah. I don't get it. Yeah, now I got one. So that's playable, but yeah, I get a little bit of latency. Yeah, by the way, this is my favorite Vectrex game. There are many games for the Vectrex, but I think this is really unbeaten yet. Yeah, no, I could play another round. I skip that now. So now I'm running the WACX emulator and simulated VGI output window on SDL at the same time. So I get a frame rate of 20 frames per second and a very reactive gaming experience. So that proves that the performance problems I face are not in the protocol, they are in the layer driver, the basic implementation. And I really hope that I can mitigate that, at least for the fast oscilloscope screens. That's where it matters with the VSD hardware. So I think that will be the next hardware I will support in my system. I think many of you know what this is. This is the Vectrex. So this is basically the machine you have seen in the emulator I demoed before. So that's the hardware where the games were running. And this hardware obviously has an XY screen. And for me, I did a little modification here. So that's this plug here. And this gives me direct access to the amplifier that drives the magnetic deflection coil and the electron beam blanking amplifier. And yeah, with this little modification, I'm able to use this Vectrex as a VGI display with my EasyLace and probably other devices in the future. And the trick here is quite simple. I have this plug here, and when I remove it, I can exchange it with a blind plug basically. So I have it here, so this. And this shortens out the connections between here, and on the one row I have the outputs from the Vectrex board, and on the other row I have the inputs of the amplifier. So that gets short-circuited then, and then if I plug this in, I have my normal Vectrex console back and can play the games from the cartridges, or I can input this and access the vector amplifier directly. So here I have the star demo running, and I hooked up my Vectrex to the EasyLace, and that's what's coming out. I get a nice vector graphics image. And yeah, I think now it's time to have a look at the laser projector and see how VGI performs there. So I guess you are already all familiar with this. So this is a scanner I pulled from a laser projector, and it simply consists out of two mirrors and two motors. The motors are called in this case galvanometers. And yeah, but essentially they are motors that consist of a permanent magnet in the middle and a coil around, and they have a feedback system at the back, so the controller knows where the mirror currently is and can control it very precisely. Technically this is a second order dynamic system, and the way the laser beam is deflected is it comes from here, then the lower mirror would display your x-axis, the upper mirror would then generate your y-axis, so that's the y deflection then. And these things are an order of magnitude slower than an Vectrex vector display or even an oscilloscope display. That's not comparable. They are much slower, and it's a lot more difficult to get lots of vectors displayed with this. I mean, a few vectors always no problem, but if your image gets more complex, it starts really to get difficult. But anyway, I would suggest now we have a look at the laser projector and see how the image looks like and how that all works. So here I have the star demo running on the laser projector. So this time it's in color. And yeah, I think I will just demo a few things, same things that you've seen on the oscilloscope screen basically. So let's now check out how the cube looks like. So this is how the cube looks like, and you can see the blue is a little bit off, so that's why my laser projector needs calibration. So the blue went somewhere, but it's not perfect. The convergence is not perfectly aligned now, but yeah, if you do not use the colors at the same time, nobody would even notice. So let's now see how the clock looks like. So this is my poor man's scope clock, and I really like this example before its simplicity. It's just basically just a printf, and that's it. So you can have with VGI you can have a clock display just by writing a few lines of C code. So that's kind of cool, I think. So and this is what happens if the HPGL to VGI demo runs. You'll see the safety inside the projectors going haywire. The noise you hear, that's the mechanical shutter. So now it's basically over. So as you can see, it's not always easy to bring vector content that runs perfectly fine on your tube, on your cathode ray tube display to a laser projector, so it can go haywire. In this case, the safety didn't like it. So and here we have the VECX demo. It's really that flickery as you see it on the camera, so the camera doesn't lie in this case. But hey, it's a playable game. I mean, yeah, as long as you don't suffer from epilepsy or something. So yeah, you really have to rely on the persistence of vision of your eyes. Yeah, so you see it's kind of difficult to display that much vectors. I mean, one could try to optimize the way the beam has to travel. So there can be some way optimization algorithm maybe. But I think we are on the right way here. So this is how Maze was looking like. And I think I have an appointment with Killer on the main hallway. And here looks like I got shot. But all in all, I think the whole thing runs fine. So maybe the names, the player names at the left side is a little bit too bright to my taste, and that also could be dangerous. I think that's the reason why the safety is hitting. You hear the noise from the safety. So here we have the shapes from the VGIoT. You see for a little number of vectors, laser projection is fine, but as soon as the image is getting more complex, things start difficult, the laser projector will hit its limits. So here we see the square that bounces off the edges of the screen. So it's in color, red, green, blue, and white at the top. So you see how far the blue is out of the convergence. So we are done with the laser projection stuff now, and before I close the video I want to know you a little bit about my future plans. This is a CRT vector monitor I'm working on. It's made out of an IBM green screen tube, so that's a tube with a beautiful green glow, and it's slightly bigger than the Vectrex tube. And I've mounted that into a wooden case, and the case can be set up in the portrait orientation. I can tilt it, so then I have the landscape orientation, and I can even use it as tabletop. So this is completely flat. It can be tilted this way and used as tabletop. And yeah, the way this works is basically I took a Vectrex apart and salvaged the deflection coil that just fits here. So I kept the deflection amplifier, not the deflection amplifier, the blanking amplifier of the original monitor. And I want to experiment with the original Vectrex deflection amplifier, and with this one, this is something I got from. It's engineered by a German guy who had an I think it was an Asteroids or Star Wars arcade board. It was arcade board with vector output, and he wanted to use that somehow. So he engineered a fast deflection amplifier that can be used with Vectrex deflection coil, and I want to use this here with that project. And yeah, it's still not finished, so there's a lot of work to do. And yeah, I just wanted to let you know. So there will be a video about this in the future when I'm done with that. So that's it for now. You now have a good overview over the VGA system, and you also know where the limitations are. And you are invited to start playing with it. I've put the download links into the video description section below. So please download and try it out. Yeah, I wish you a Merry Christmas and a Happy New Year. So take care and goodbye. See you soon.